This vodcast is on applications of aqueous equilibria. So in the previous chapter we discussed acids and bases and how weak acid and weak base equilibria can be established and calculated. So now we're going to take it to the next step. First thing we need to talk about is titration curves. And titration curves are a graph where we're showing the pH with respect to the concentration of the solution that we are adding to our known acid or known base. So we call that a titration curve because as we add each amount, we plot a new point for the new volume of the solution that's added, and we can see how the pH changes over time of the solution being added. There's a point in a titration curve in which the amount of acid and base in the solution is equal, and we call that the equivalence point. So if we're graphing it, we can find the equivalence point by seeing where the slope of the graph changes direction. But if you were to do the titration with an indicator, you don't always hit the equivalence point because you are waiting for a color change. So you might be a little bit beyond the equivalence point, and so that's referred to as the end point, where you've missed the equivalence point but you're kind of close enough. The reason why you can miss and be close enough is because this is the shape of the titration curve. So if you look, you see that the equivalence point is right here. So what's happening is you start with an acid, and obviously we're starting with an acid because see, the pH is very, very low. So the acid has a very, very high concentration. So as we add the base, it's hardly doing anything as far as removing any of the acid from the solution, because you have to remember the pH scale is based on powers of 10. So a pH of 1 has a massive amount of hydrogen ions in it. So as we add the base, it's going to have very little effect on the total amount of hydrogen ions. So the pH changes very, very slowly in the beginning. But then as we start to get closer and closer to the equivalence point, you can see that the curve begins to change its shape very, very quickly, because now the amount of base you're adding is actually having a huge effect on the amount of hydrogen ions in solution. So one drop will take you from about a pH of 4 here all the way up to about a pH of 10. And right in the middle of that vertical spot where that drop changed the pH by that drastic amount is the equivalence point. And then after that, as we keep adding and we get to the top of the curve, you see that it levels off again because now there's so much base in there that adding more drop by drop, or small amounts of milliliters by small amounts of milliliters, has almost no effect. So before the titration, all we have in here is hydrochloric acid, although it's leaving the water out. And then as we begin to add sodium hydroxide, it's going to take out some of the H plus ions and turn them into water. And as we reach that equivalence point, that's where the H plus has been completely neutralized by the OH minus. And then after that, you can see that we're going to have some base left over that does not have any acid left in the solution to react with, so that will remain, and that's why your pH continues to stay very, very high. If we started with a strong base and titrated it with a strong acid, we would just start with a high pH and it would go down. So you can see it's kind of the flip of the strong acid, strong base. When we pick indicators that are in that vertical region. So if we were to do a strong acid, strong base titration like hydrochloric acid and sodium hydroxide, we could use phenolphthalein, where even though its color change isn't at the equivalence point, it's still in that vertical section, so we can still use that effectively to determine when we've neutralized our solution, because that one drop is going to take us all the way through that region. Or we can even use methyl red, which is a different indicator that changes from a reddish to a yellowish color, then that's down by the 4 to 6 range, because again that's still in that vertical section. The titration curve will change its shape though if we're going to do a weak acid strong base titration or a strong acid weak base titration. And so when you put a weak acid in there, the pH will be higher than it would be if you had a strong acid, because again it's a weak acid, so not all of it dissociates, so a very small percentage of hydrogen ions are actually present in solution. So most of the weak acid is still in its molecular form. So as you drop the strong base in the beginning, it removes all the hydronium ions from solution, but that's going to drive an equilibrium now because there was more acid in there that had the ability to dissociate. And so now more of that acid will dissociate. So if you look at the equation for the dissolving of acetic acid, you could see that if we pull out these hydrogen ions over here by adding the base, that it's going to lower the concentration of this, and Le Chatelier says then that the reaction is going to shift right to establish the new equilibrium, and when it shifts right, it means more of this acetic acid is going to be converted into the hydronium ions and acetate ions. So eventually a new equilibrium will be established if you just add a few drops or a milliliter and leave it. And the more base that you add, the more the conjugate base of your weak acid is created as well. So that's important to note. So what we end up with is a region in there where we call it the buffer region. And the reason is that once you have significant amounts of conjugate base in the solution, the pH will begin to change at a much slower rate when you add more base, because adding base, it's already somewhat basic at that point. So if we add acid to it, the conjugate base would neutralize that also, preventing a pH change in the negative direction. So what you have is a situation where by adding acid or base, your pH is not going to be affected very much by it. So this is called a buffer, since adding small amounts of either an acid or a base won't change the pH. So it kind of protects the solution. At the point where an equal amount of acid and base are added, the conjugate base is the only ion left in solution that's going to affect pH. So in the case of this weak acid strong base titration, we're going to have an equivalence point that's greater than 7. The same would be true if we did a weak base with a strong acid. In that case, though, your leftover after you've reached the equivalence point is going to be the conjugate acid of that weak base. So therefore, the pH at the equivalence point for a weak base strong acid titration will be below 7. So here's the idea of the buffered solution. So you really get to the point where you have equal amounts of your conjugate base and your acid, and so at that point you are perfectly buffered because now you have both acid and base in there, so no matter what you add, it's going to adjust the equilibrium. If we added hydroxide, we're going to react more with the hydrofluoric acid and create more fluorine ions, and if we added acid to it, then we're going to pull out more of the fluoride ions and produce more of the hydrofluoric acid. So no matter what we add to it, the solution will adjust to absorb it. So here's our situation where we have a weak acid being titrated by a strong base. And so you see we have this quick vertical up. You're starting at a higher pH because the weak acid had very little dissociated. You have this quick vertical up, but it very quickly levels off when you reach that buffer region. So this is the buffer region. This whole area right in here is the buffer region because that's where your pH change is minimized by the fact that you're creating the conjugate base to go along with your acid. Eventually, though, you're going to add enough base to take all of that acid out, and you no longer can establish an equilibrium with that conjugate acid-base pair because there is no acid left. The strong base has completely neutralized all of it. So what's left in the solution then is when all the hydroxide's been used up, is that conjugate base is in here, and you can see that your equivalence point here is over 8. So this is an example for acetic acid. So before you have acetic acid, and then you have some acetate ions with the sodium hydroxide being added, and then you're going to have very little acetic acid left later on, but still some, and then finally when you reach the equivalence point there's going to be none left at all, and it's all going to be the acetate salt. So if you look at the Kas for different acids, you could see that if you use the same volume of acid with these different Kas, that you're going to have a different buffer region in a different spot depending on what the Ka is. but your final ending place is going to be the same regardless of what acid you use, because at that point there's going to be no acid left in solution. So the higher the Ka, you can see the higher the equivalence point, but that equivalence point still takes place before your pH of your solution begins to level off up at a pH of 12. So they're all in basically that same vertical region. So here, if we wanted to do an acetic acid titration, we could use phenolphthalein because it's still in that vertical range, but we could not use dimethyl red because dimethyl red is outside of that vertical part approaching the equivalence point. So methyl red would change color before we've actually reached our equivalence point, so that would not be good to use. If you have a polyprotic acid, the first one is the strongest, but in this case it's phosphorus acid, which is a weak acid, and each of the other acids that you produce after that is going to be even weaker, and the Ka is going to be significantly smaller. But you can see that you're going to have 3 different equivalence points essentially for the removal of each of those ions. So there's several buffer regions here. Another thing that comes into play in aqueous equilibria is the common ion effect. So if you add a strong electrolyte in a solution that has a weak one, and they both have the same ion, and we're using the example, the acetic acid, and we add sodium acetate to it, then the weak electrolyte will end up ionizing less than it would if it were alone. And again, this goes back to Le Chatelier. So if we were to add acetate ions to this by adding sodium acetate, then these acetate ions, there's going to be too many of them, and it's going to shift the equilibrium left, which is going to cause some of those acetate ions to react with the acid in the solution, the hydronium ions in solution that is, and produce more of the acetic acid, which means that less of the acetic acid will actually be in solution at that point. So you ice this the same way for the common ion effect, and you'll practice this in class, except now you'll have a concentration of another ion, not just the acid or base concentration that you're trying to make the solution of. Another thing that there is the solubility product, and this works because dissolution is an equilibrium process. So as salts are dissolving, they're establishing an equilibrium where the ions are going into solution, but other ions that are already in solution are still colliding and moving with each other, and sometimes when they collide, they will attract to the ion that they collide with, and they'll stick together and recrystallize into the salt. So there's this common constant balance going on between the salt dissolving and the ions dissociating and the ions reassociating and recrystallizing. So the KSP is the mathematical equivalent of the product of the concentrations of the ions. And we call that the solubility product constant. It's essentially the products of the equilibrium expression of law of mass action. And since it's a salt dissolving in water, there is no bottom to this. So what the KSP really measures is the quantity of solid that dissolves to make a saturated solution. So the higher the KSP, the more solid will go into solution before it saturates it. The lower it is, the less will. So basically we can cut off different values for the KSP and say, well, that's where this is soluble versus insoluble versus slightly soluble. And we can use the KSP to determine the solubility rules, and so then we can use that in what's called qualitative analysis, which is when you're presented with an unknown solution or an unknown mixture and we want to know what ions are in it, we can do a series of reactions to identify what those ions are. So using solubility rules based on the KSPs, we can add different chemicals to it and cause selective precipitation where only one ion comes out and the others remain in solution. The amounts of those ions, though, are not determined because that would be quantitative, and that's why this is called qualitative analysis, because it's just, is that in there or not? We've done lots of these experiments in your chemistry classes to this point where we just did reactions and said, yep, that happened, or yep, this is what we produced, just by looking at whether or not we got a color change or precipitate or whatever. Okay, we could take it another step and do quantitative analysis. That's going to require a much more controlled and significant amount of work. So here's an example of a flow chart of how we can start to identify whether these ions are in solution. So see at the top we have a solution containing unknown metal cations, and you can do this for anions too. There's a similar chart for that. So if we add hydrochloric acid, all the metal ions that are highly reactive are going to react with that and stay in solution, and the ones that aren't reactive metals are actually going to come out of solution, like the silver, the lead, and the mercury, where you get the insoluble chlorides. And so then you can take those remaining cations, if you haven't identified what you wanted to identify yet, and you add hydrogen sulfide gas. When you bubble that through, sulfides for a lot of them are insoluble, so you'll get a lot of other things that come out there, like copper sulfide and cadmium sulfide, etc. There might still be ions in solution, so you could add ammonium sulfide, and when you add that, you're going to get hydroxides out of that, because ammonium sulfide is going to have some base properties to it. Or you might get some other sulfides in there. You see zinc sulfide and nickel sulfide is there. And then if there's anything left, you can go and add ammonium hydrogen phosphate and ammonia, and when you add that, you'll precipitate out some phosphates, and I'd be able to identify it that way. And then if that hasn't created your precipitates yet, then you know that the rest that's in there are the alkali metals. So it's just a series of reactions that you could go through to separate the ions into groups and be able to say, okay, yeah, we have copper in here because that reacted after the second reaction, but we didn't have anything from group 3. But then when we did the fourth reaction, we ended up with phosphate, so there must have been calcium in there, barium in there, or something like that. So this is the general gist of all the things in aqueous equilibria, and we will spend some time in class looking at all these things, from buffers to weak acid titrations to solubility products, and we will try to clarify this as much as possible.